Welcome to this course titled Advanced Mathematical Methods in Chemistry. This is going to be a 12-week course, and today we will start with the first week. And the topics that we are going to discuss in this week are related to vectors, vector spaces, vector operations and vector calculus. Today I will start talking about vectors, vector spaces, the idea of linear independence and basis vectors. So, all of you are familiar with vectors in some form. You might have heard of vectors as objects that have both a magnitude and a direction. So, for example, you could have a vector that is shown by an arrow in space. So, it has both a length which represents the magnitude and a direction which is represented by the direction of the arrow. Now, this vector, if you denote this vector by the notation r, okay, and you write a vector on top, then there are different ways in which you can represent this vector. For example, I could write r, okay, and assuming that this is in a two-dimensional space, I could write it as x times I plus y times j. This is a vector 2 dimensions. Or you could have a vector in 3 dimensions, which you might write in this form x I plus y j plus z k. This is a vector in 3D. So, these are examples of how you write vectors. Now, you could write this equivalently. You could just write this in a different notation. For example, this you could write as just instead of this r vector, you could write it as x times y, x comma y, okay, which is a way of writing which instead of writing this I and j every time, you just write it as x comma y. So, x and y are called the components of the vector. Okay, x is the x component, y is the y component of this vector r. Similarly, in 3D you might write r, so it is often denoted as x, y, z, where x, y and z are the components of this vector. So, you do not have to explicitly write this I, j and k. In some cases, we will also use a notation where this is represented as equivalently represented as a column vector. So, this might be written as x, y or as a column matrix. So, this is a matrix representation of the vector. So, the same vector can be written in different notations. So, you can write it as in this I, j, k notation, or you can write it in x comma y comma z, or you can write as a column matrix. So, all these are notations for vectors, and in various cases you would be using one notation or the other as convenient. Now, the nice thing about writing vectors in these forms is that you can immediately see how to add vectors. So, suppose you had one vector, I will show it in 2-dimensional space. Suppose you had a vector r1 which had components x1 and y1, and you had a vector r2 which had components x2 and y2. Okay. Then you can have a vector r1 plus r2 which is a vector addition, okay, and this vector addition will yield a vector with 2 components x1 plus x2 and y1 plus y2. So, what you do when you add vectors is to add them component wise, and similarly I can do this in 3 dimensions also. I will not show this explicitly, okay, but vector addition is something that you can easily do, especially using this notation. Another important operation on vectors is called scalar multiplication. Okay, where you take a vector, for example, you could take a vector r which is denoted by x, y, and a scalar. A scalar is nothing but a real number. And let me call the scalar c. Okay. So, if you had a scalar c and a vector r, then you could multiply c times r, okay, which gives you another vector. So, this is a vector, and what are the components of this vector? Okay, the components of this vector are C x and C y. Okay. These are these operations which are namely vector addition and scalar multiplication are extremely easy to do in this notation. Okay. And in fact, these are two operations that actually end up defining vectors. So, vectors are defined on the basis of these operations, and we will see that in a minute. We will look at the idea of what is called a vector space. Vector space, and to motivate this idea, let us consider 2D first. 2D. Okay. So, now in 2D you show a vector by an arrow. So, let me show the entire x y plane. This is the entire 2D space, okay, 2D coordinate space, and this entire space of all coordinates will be related to what is called a vector space. So, how do we understand what this vector space is? Now, if you take any vector in this 2D, okay, any vector can be represented by an arrow, or it can be represented by a point x y, the coordinates of that point are x y. Okay. So, now suppose you take the set of all vectors, all possible vectors in 2D. Okay. So, this is basically equivalent to the set of all pairs of real numbers x and y. So, you take any two real numbers x y, that can represent a vector, okay, and the set of all pairs of real numbers represents the set of all possible vectors, and this is a vector space. Vector space, the word space is used to denote this entire set. So, the set of all possible vectors is called a vector space, and this is the usual 2D space. Okay. Similarly, we can have we can do in 3D also. So if you say what is 2D space or 2D vector space, okay, this is the set of all possible x y, okay, such that x and y are real numbers. And this constitutes a vector space, and in particular it is a real vector space. Okay. So, it is a real vector space because we insisted that x and y should be real numbers. Okay. So, the set of all possible vectors in 2D constitutes a real vector space, okay, and this is a two dimensional real vector space. Now, there are some characteristics of this vector space that basically those go back to the two operations that we talked about last time. So, addition of two vectors in the vector space gives another vector. Okay. So, if you add any two vectors, you get another vector which is also in the vector space. Similarly, scalar multiplication of a vector. So, you can take a vector and multiply it by any scalar and you will get another vector. That gives another vector. These are easy to see because you can just take any vector, multiply it by a scalar, you will get a different vector, and so that vector will also be in the same space. Okay. So, this is the main characteristic of the vector space, that you can add any two vectors or you can multiply by a scalar, okay, and you get another vector. Okay. So, and there are certain other fairly obvious things like there is something called a 0 vector, okay, 0, and there is something called an inverse vector. So, A plus any vector A plus a vector minus A gives you 0. So, the minus A is called the inverse of A, additive inverse. Okay. So, these are certain, and these are very obvious. I mean, for suppose you look at this vector, okay, this vector that is shown here, then you can easily see that an inverse for this vector would look something like this. Okay. So, if this is r, then this will be minus r. Okay, it is just a negative of that. So, that is the additive inverse, such that you add up these two and you get the 0 vector. Okay. So, these are things that that are also vectors. So, the condition for something to be a vector space is that you take the collection of all possible vectors, okay, such that you add any two vectors, you get another vector which is also in the vector space, and the vector space has a 0 vector. Okay, because I added A and minus A and I got a 0, which is, I should emphasize, this is a 0 vector. Okay. So, 0 vector is also a vector in the space, okay, and also there is an inverse, additive inverse for every vector. So, these are the basic axioms which define something called a vector space, and the advantage of defining something like a vector space is that you can now extend this to any dimensions. You can go to 2D, you can go to 3D, but you do not need to stop there. You can go to 4D, you can go to, can be extended to arbitrary dimensions. Okay. And so we have seen 2D, we have seen 3D. So, for example, if you want 4D, okay, 4D you can just write x, y, z, w. You can just have 4 variables. So, a collection of 4 numbers, okay, 4 scalars would form a 4D vector space. Okay. So, this is this turns out to be fairly useful, and it has lot of applications, as we will see. Okay. Now, we can we will come to a formal definition of what we mean by the dimensionality, okay, in a few minutes. Okay. But before that, we will introduce the idea of linear independence. So, the next idea is the idea of linear independence of vectors. So, what does linear independence mean? So, suppose you have a set of vectors. So, suppose I will just take for example, I will just take given a set of n vectors. Okay, I will denote them by r1, r2, r3 up to rn. Okay. I am not saying anything about the dimensionality of the space or anything. These are just n vectors in some vector space. Okay. So, if you are given a set of n vectors, okay, then you can ask, are these linearly independent? So, these vectors are said to be linearly independent if the condition C1 R1 plus C2 R2 plus and so on up to Cn Rn equal to 0. Okay. So, for real numbers C1, C2 up to Cn. So, if this condition implies that C1 equal to C2 equal to C3 equal to up to Cn equal to 0. So, if this condition necessarily implies that C1 equal to C2 and so on equal to 0, okay, then the vectors R1 up to Rn are said to be linearly independent. So, now a few things I should mention. Okay. So, what we did here, we multiplied it by a scalar C1, okay, and then we took vector R2 multiplied it by another scalar C2, okay, and we added up these two vectors. Similarly, we did that for all the remaining vectors. This is called a linear combination. So, what we did here was took a linear combination of vectors R1, R2 up to Rn. Okay. So, this C1 R1 plus C2 R2 plus up to Cn Rn is called a linear combination of vectors, okay, vectors R1 up to Rn. Okay. So, we took a linear combination and we said that if this linear combination yields, and again I was a little sloppy, this should be a 0 vector, because linear combination of vectors gives you another vector, because all we did was we multiplied by a scalar and we added it. So, we should get another vector. So, if this gives you a 0 vector, okay, then if these vectors are linearly independent, then this can only be satisfied if each of the C1 up to Cn equal to 0. Okay. So, so what that means is that the only way you can have this equal to 0 if all these are equal to 0. Okay. Now, suppose vectors were R1, R2 up to Rn were not linearly independent. Okay. So, if they were not linearly independent, okay, or in other words they are linearly dependent, okay, then obviously then C1 R1 plus C2 R2 plus up to Cn Rn equal to 0 for some set such that C1 C2 up to Cn such that not all of them are equal to 0. Okay. So, for example, suppose C1 not equal to 0. Okay. So, just suppose we can take any we can do with any of these scalars, but suppose C1 was not equal to 0. Okay. Then what you could do is you could write R1 as minus C2 R2 minus C2 by C1 R2 minus C3 by C1 R3 and so on up to minus Cn by C1 Rn. You could write it as this. We already said that C1 is not equal to 0. So, C2 by C1 is a real number, C3 by C1 is also a real number and so on. So, all these are real numbers. So, what we did here is we expressed R1 as a linear combination of R2, R3 up to Rn. Okay. So, what I want to tell you is that when vectors are linearly dependent, when they are not linearly independent, then you can express one of them as a linear combination of the others. Okay. So, what we did, what this rather obscure looking condition for linear independence implies is that you cannot write any vector as a linear combination of the others. Okay. So, if you cannot write any vector as a linear combination of the others, then the vectors are said to be linearly independent. So, for example, if you take the usual, let us say in a 3D space. Okay. So, vectors I is also a vector, okay, j and k are linearly independent. Because if C1 I plus C2 j plus C3 k equal to 0, okay, this implies this can only be true if C1 equal to C2 equal to C3 equal to 0. So, if any of these are non-zero, you cannot, these cannot add up to 0. Okay. So, therefore, I, j, k are linearly independent vectors. Okay. Now, what would be an example of vectors that are linearly dependent? Okay. So, for example, we can take 3D vector space again. Okay. So, let us take vectors I, j, let me take a vector j plus k and let us say 2 I plus j plus k. Okay. So, I took these 3 vectors. So, I have one vector which is just I, the other vector is j plus k, and the third vector is 2 I plus j plus k. Now, clearly I can write 2 I plus j plus k as 2 into I plus 1 into j plus k. So, I wrote this as a linear combination. I wrote the third vector as a linear combination of the first 2 vectors. Okay. So, I multiplied the first vector by a scalar 2 and the second vector by a scalar 1, and I added them up. So, I took a linear combination of these 2 vectors and I got the third vectors. So, clearly these are linearly, so implies vectors are linearly dependent. Okay. So, the idea of linear independence and linear dependence is extremely important for in vectors. Okay. And the if you take any vector space, there are some there is a maximum number of vectors that can be linearly independent. Okay. Any vector space has a maximum number of linearly independent vectors. Okay. So, it has a maximum number of linearly independent vectors, okay, and this is called the dimensionality. Of the vector space. So, what that means is that if you have a 2-dimensional vector space, you cannot have 3 vectors that are linearly independent. So, in a 2-dimensional vector space, you cannot have 3 linearly independent vectors. Similarly, in a 3-dimensional vector space, you cannot have 4 linearly independent vectors, 4 or 5 or 6 or any number greater than 3. So, the maximum number of linearly independent vectors is equal to the dimensionality of the vector space, and this is fairly obvious to see. Okay. So, you can just take any 3 vectors in 2D space and you can easily show that one can be written as a linear combination of the other 2. Similarly, you can take any 4 vectors in 3D space and show that one can be expressed as a linear combination of the other 3. Okay. But the point is that the idea of linear independence, okay, is related to the dimensionality of the vector space. Now, another way to say what the dimensionality of the vector space is to introduce the idea of basis vectors. So, your basis vectors Okay. So, basis vectors are a set of vectors which are A linearly independent and B span the entire vector space. Okay. What does it mean by span the entire vector space? So, that means any vector can be written as a linear combination of basis vectors. Okay. So, basically if you know the basis vectors, then you can take a linear combination and you can construct any vector in the vector space. So, that is what it means to span the entire vector space. So, if these two conditions are satisfied, then the vectors are said to form a basis and these are called as basis vectors. Okay. And now you will see that the dimensionality is equal to the number of basis vectors. Okay. So, the number of basis vectors is equal to the dimensionality of the space. Okay. So, for example, if you take a 2D space, okay, you can choose basis vectors as I and j. Okay. So, any vector x comma y can be written as x I plus y j. Okay. I did not mention this, but I can write I as 1 0 and j as 0 1. Okay. I can write it in the same notation that we have been following. I would be written as 1 0 and j would be written as 0 1. So, you can write any vector x y as a linear combination of I and j, x times I plus y times j. Okay. So, these form a basis, they are linearly independent. Okay. And you cannot have more than 2 linearly independent vectors in 2D space. So, they form a basis and you can write and they span the entire vector space. Okay. Now, similarly in 3D space, basis vectors are I, j, k. This is one possible choice of basis vectors. Okay. Now, importantly, this is extremely important to note and I am emphasizing this here. So, basis vectors are not unique. Okay. So, this is a very important idea. Okay. In fact, if you take 2D space, if you take any two linearly independent vectors, they can form a basis. Okay. Any two linearly independent vectors in 2D space, okay, which span the entire space will form a basis. Okay. And in order to span the vector space, they should be linearly independent and one of them should not be 0, and that is it, you are done. You can take any two linearly independent vectors and you can show that they span the entire vector space. Similarly, any 3 linearly independent vectors in 3D will span the vector space and so they can be used as a basis. So, for example, in 3D I can consider instead of I j k as a basis, I can take I plus j k I minus j. I can take these 3 as a basis. Okay. So, this is also a valid basis. And you can check that these are linearly independent, and because the dimensionality of the space is 3, okay, in 3D space these will span the entire space. Okay. So, the idea of basis vectors and linear independence is actually extremely useful, and what we will see in the next lecture is how this allows us to generalize to vectors of arbitrary dimensions.